Okay, welcome to our 2.8 concepts video, where we're going to be talking about something called implicit differentiation. And this concept's not really an application of derivatives, but more just another strategy we have for taking derivatives of more complicated equations. Equations such as this. There's a reason why I'm using the word equations and not the word function, because maybe some of you guys recognize an equation like this. It comes from this form, x squared plus y squared equals r squared. And this is the equation, this is the general form of the equation for a circle. So this right here is a circle with radius 3. And once again, this is not a function. A circle is not a function because if I pick some x value inside the circle, then that gives me two possible y values that I could get out from that single x value. The reason why is if you actually try and solve for y, square rooting introduces that possibility of getting a positive value or a negative value, right? Because either of those values will work, unless I get two possible outputs for a single input. But the fact remains that this equation still gives a relationship between an x and a y value. It still shows that y depends on x. And therefore, I should still be able to find how the y changes if I change my x value. In other words, I should still be able to find a derivative. The derivative of y in terms of x, or how does y change as x changes? The question then becomes, how do I take a derivative if I don't know exactly how y depends on x? Well, it turns out this is very closely related to the chain rule. And here's why. One of the big things to remember with implicit differentiation is when we use implicit differentiation, we don't bother solving for y. Because once again, we could run into problems trying to solve for y where we have two possible answers, or we could run into situations where it's impossible to solve for y. So that's one of the first things to know about implicit differentiation is we don't bother solving for y. We go ahead and take the derivative as it is. So I'm going to take the derivative of this right now. D over dx represents taking the derivative in terms of x. Well, based off of some of my derivative rules, I know that if I'm taking the derivative of two functions being added together, that means I can take the derivative of those two functions separately and then add them together. And it turns out that also applies over equal signs. So now let's zoom in on each of these three pieces. First of all, how do I take the derivative of x squared in terms of x? Well, since this right here is simply a function of x, I can take the derivative like normal. What's the derivative of x squared? It's just 2x. So there's nothing complicated about taking the derivative of this piece because it's a function of x. It's already in terms of x. Well, let's skip this piece for now. We're going to come back to that piece, and let's move to the other side of the equal sign. How do I take the derivative of 9? Well, 9 doesn't depend on x, but it also doesn't depend on y. 9 is constant. So as x changes, how is the constant 9 changing? It's not changing, and we already know how to take the derivative of constants. We just get 0. So that is also still true for implicit differentiation. So now we have to come back and look at this middle term. How do I take the derivative in terms of x of a function that's in terms of y? Here I have y squared, not x squared, I have y squared. How do we take the derivative of this when we're taking it in terms of x? So this is where the chain rule comes in. With a little bit of algebraic manipulation, I can change this to the following. Right? We remember seeing something like this when we talked about the chain rule. This is just me manipulating this fraction to get this. If I wanted to simplify it back through again, I could just cancel those dy's and you're back to d over dx. But if I don't cancel those dy's, tell me about this term. Well, this is the exact term that we're looking for. This represents the derivative of y in terms of x, and another way I could write that is y prime. Right? It's the derivative of your y function in terms of x. And that's exactly what we're looking for. So that's good, that's going to end up being part of my function. But what's important about this piece? This notation now means I'm taking the derivative in terms of y. How is the function changing as y changes? Right? We saw that earlier with d over dx. d over dx just means I'm taking the derivative in terms of x. So if I switch that to d over dy, I'm now taking the derivative in terms of y. So how does that help me? Well, I can come over here and I can switch d over dx into dy over dx times d over dy evaluated for y squared. Now that means I can take the derivative of this in terms of y. What's the derivative of y squared if my variable that I'm looking at is y? It's just 2y. So I'm left with 2x plus, I could keep this as dy over dx, or I could also rewrite it as y prime. Either one. I usually like doing y prime because it's less writing, but you can keep it as dy over dx if you want to. And then like we said, the derivative of y squared is just 2y. Now where do we go from here? Well, once again, what are we looking for? We're looking for how y changes in terms of x. We're looking for that derivative. We're looking for y prime. So from here, I can just solve for y prime. And I get negative 2x over 2y, which simplifies to negative x over y. And I want to point out something here. You'll notice that this derivative is in terms of both x and y. And that's normal for implicit differentiation because we started with a function that was in terms of both x and y. But that's my derivative. That does mean, though, that when we use implicit differentiation and then we look at a specific point, we will need both the x and the y value for that specific point. So let's summarize. When I use implicit differentiation, things to keep in mind. First off, don't solve for y. And second off, if you end up taking the derivative of some function that's in terms of y, like that y squared that we ran into over here, when I'm trying to take the derivative in terms of x, but it's a function in terms of y, what did we end up doing? We ended up taking the derivative like normal, but then multiplying it by dy over dx when I was done, or y prime. And those are kind of the two big ideas with implicit differentiation. So now let's talk applications. One major application of implicit differentiation is something called related rates. You may have heard of this before. There's going to be a couple of problems on the homework concerning related rates. And the big idea of related rates is you might have an equation dealing with lots of variables, but you're assuming that every single one of those variables depends on time. An example of this is, say you have a pool that you're filling with water. I can measure the volume of the pool using the formula for the volume of a cylinder, but if I'm slowly filling it up with water, that means these variables are changing as time passes. The volume of water in the pool is changing as time passes. The height of the water in the pool is changing as time passes. So all of these variables depend on time. Therefore, I can take the derivative of this in terms of time to analyze how exactly they change as time passes. So we'll go through an example of one of these in the examples video, but the concept behind this is still the same. You're just taking the derivative and you're using this process as you take the derivative in terms of time. So go ahead and try out the homework, and we'll go through a couple of the problems in our examples video whenever you end up having questions. Good luck.